Hello, I'm Michael Poplawski, and I'm here with my colleague Shat Pratoomratana, and we're here to talk to you about how can connected lighting systems be configured to respond to OpenADR 2.0 price signals. Now that's may sound like a pretty narrow topic, and so I thought I would initially introduce the reason we're doing this research. So why are we interested in lighting system responses to OpenADR signals? Well, at a high level, the growth and penetration of renewable energy and distributed energy resources, otherwise known as DERs, has led to increased operational reliability and resiliency issues on the grid, and therefore the need for new so-called grid services or means for mitigating these issues. We think, and others think, more flexible DERs can provide those grid services and be part of the solutions. And one type of flexible DER is a building. Buildings have many systems that have varying demand, and if they could be flexible in when and how much demand they are requiring, they might be able to help mitigate, grid issues as just discussed. However, building system in general and lighting system in particular, flexibility is not well understood, and lighting is often thought to not be well suited for providing grid services, in part because people think, well, you can't pre-light or pre-light a space like you can pre-cool or preheat a space with an HVAC system, or you could preheat a water heater. However, commercially available lighting systems are increasingly becoming more connected, and this is important because this connectivity makes them amenable to receiving grid signals and exercising whatever flexibility they have. So these connected lighting systems are now widely available, and they make they're making an increasing amount of marketing claims. In general, these systems have been enhanced to provide functionality beyond lighting service. This functionality is typically the result of increased integrated intelligence, integrated sensors, and more modern network communication interfaces. The net combination of that are lighting systems that can produce data and share that data with other lighting and non-lighting systems. And this is where the marketing claims really start to appear. What are the use cases for that data? Some of the simpler ones we've been aware of for a while, using occupancy data, for example, to turn lights on and off, or perhaps set back thermostat settings for specific HVAC zones. But some newer use cases are using reported energy data and occupancy data together to analyze, improve, and possibly improve energy performance, and the use of device electrical characteristic data to identify, categorize, and possibly predict faults. Other use cases people talk about are monitoring space utilization, noise, air quality, and other environmental characteristics. So the goals of our research are to understand, can lighting provide unique or substantial grid services? And, drilling down a little deeper, what grid services does lighting have the most potential for providing? How can that potential be quantified? And, what's the potential then for commercially available lighting systems? So what's on the market today to provide these grid services, and what are their current limitations? And that really is going to be the focus, that last question, of the remainder of this talk. And with that, I will turn it over to Shat.
All right, thanks for that introduction, Michael. And so I'll be starting with a little bit of background so we can get to know a little bit more about this topic. And in today's presentation, we're going to focus on the development of a means for evaluating commercially available lighting systems. And in order to start doing this, we had to ask a few questions. So our first research question we wanted to ask is, how might lighting systems be expected to respond to OpenADR signals? And then what signals are defined in OpenADR 2.0b, and how are they intended to be used? Which OpenADR signals are appropriate for connected lighting systems to respond to? And what configuration parameters might be needed for CLS to appropriately respond to each appropriate OpenADR signal? And for today's presentation, the signals that we'll mostly be focusing on are pricing signals. And before we get into that, just a little bit of background. And so Michael mentioned lighting in buildings utilizing their flexibility. And one of the most common ways that flexible loads have been utilized is in the form of demand response or DR programs. And demand response, it's a way of balancing supply with demand by making power adjustments at the demand side rather than at the supply side. For demand side loads to make adjustments to their power output, utilities need to inform customers of the grid and market conditions as part of their demand response program. And so demand response programs, they're classified by the Department of Energy as either dispatchable or non-dispatchable. The dispatchable programs have loads respond directly to signals from the grid operator, utility, or third-party aggregator, while non-dispatchable programs have loads that respond at the discretion of the building owner in response to pricing signals. And since we'll be talking about pricing signals today, I think it will be useful to just go over a few of the different ways that pricing can be used. So critical peak pricing, it's a standard flat rate, but with elevated pricing during critical times. Real-time pricing has pricing that fluctuates in real time based on generation cost. And time of use pricing has fixed periods with price that is based on the typical daily demand. And so these price signals need to be communicated between the utility and the loads in some way. And one way this is being done is by using a communication protocol called OpenADR. The OpenADR protocol, it was created with automated demand response programs and DER management in mind. It has a more inform and motivate philosophy rather than a command and control one. And this type of philosophy, it actually can lend itself well to lighting because allowing the owner operator to determine their own response will enable them to maximize the flexibility of their lighting system while still satisfying occupants' lighting needs. And so OpenADR, it has two main actors, the virtual top node or VTN and the virtual end node or VEN. And the VTN, it's an information exchange server, which is responsible for creating and publishing information about upcoming DR events, such as pricing information. And it usually sits at the utility or aggregator level. The VEN, it's a logical endpoint, and its responsibility is to receive the DR event messages and information from the VTN and then translate that information into something usable by outside systems. And it's typically an interface between the utility and the loads. And so a single VTN can connect to many VENs, but a single VEN can only connect to one VTN at a time. OpenADR, it actually contains 10 unique signals. All of the signals were explored in the full study, but to limit the scope and due to time for this presentation, we'll only be talking about the three circled in blue that have to do with the price of electricity. And so we had to implement a test setup, and the one we implemented here, it creates an OpenADR event, which is then, and then it uses a Python script to emulate a building or lighting energy management system, which then creates an adjustment to lighting demand in response to the OpenADR price signal. And so we need a lighting load profile for a building, which describes how the lighting load changes throughout the day. And the lighting load or the building that we used is a DOE prototype building, the medium office building. The nominal load profile is based on this prototype. And the minimum and maximum loads are determined by considering daylighting and recommended daylighting practices and codes. And these lighting load profiles put together, they define the flexibility range of the system, which changes throughout the day. And so once we have our load profiles defined, we need to have a way to describe the relationship between the price of electricity and the power output of the lighting system. So in the top, we can see our building lighting load profile that we described previously, and the bottom plot shows what we are calling a demand curve, which relates the price of electricity on the x-axis to the power output of the lighting system on the y-axis. And in order to interpret these demand curves, we can use an example. So if we look at hour 13, we can see that we already know what our max, nominal, and minimum load are, shown in the purple circle at the top. And knowing these values, we can actually choose at what prices those values occur. So we can define a minimum, maximum, and mean price, which is shown as the vertical dashed lines in the bottom. And then we can set the maximum load to the minimum price, which are the green lines, the nominal load at the mean price, which are the blue lines, and the minimum load at the maximum price, which are the red lines. And so we can consider these points the inflection points, which are then connected by lines to form a completed demand curve. And so any price outside of this price range that's been defined will not result in any more load change. And this is to prevent the lighting load from going outside of its flexibility range. And so the inflection points in this example, they depend on the max, nominal, and minimum load values, specifically at hour 13. But at different times of the day, the minimum and nominal load values are actually different. And so this actually results in there being a unique demand curve for each fixed power level and the time period for which it applies. So for example, the nominal and minimum loads are different between hour 13 and 17, but they're still set to the same mean and max price, which results in a separate demand curve. And so this concept of a demand curve is the way in which we're going to be exploring how to configure a connected lighting system to respond to OpenADR signals. So the three signals that we want to look at, that we're looking at today, are electricity price, energy price, and bid price. The electricity price signal, it's a basic electricity price that's described as the cost of electricity and expressed as dollars per kilowatt hour. Energy price and bid price signals also convey the same pricing information, but the energy price signal may include pricing factors beyond those in traditional electricity pricing. And the bid price signal, it's a price signal with the caveat being that the value of the signal is derived from a bidding process defined outside of the scope of OpenADR. And so without the context of a particular DR program or bidding program, these signals, we are going to consider them equivalent for this analysis. So in the top plot, we can see our previously shown load profile with a few additions. So the addition of the pink line, it shows the incoming signal as the price of electricity over time, with its value being shown on the secondary y-axis. And the dashed black line in this figure shows how the load will deviate from nominal in response to a changing price. And the magnitude of this deviation, it is controlled by the demand curve that is drawn in the bottom subplot. And so there are multiple demand curves, one for each fixed power level and the time period for which it applies. And it's constructed like the example demand curve by defining inflection points. So the max power at the min price, nominal power at the mean price, and the minimum power at the max price. And in this case, the mean price is 3 cents. The inflection points are then connected by straight lines to make what we're going to be referring to as a linear demand curve. And one last addition to this figure are the teal lines in the bottom plot that represent cost. And the reason we want to observe cost is in order to use it as a metric for determining demand curve performance. So in other words, if cost is to be accounted for in the design of a demand curve, observing the cost will allow us to evaluate how well the demand curve actually controls for cost. And each individual demand curve, it has its own cost curve, and in order to actually calculate the cost, basically each point on the demand curve, you multiply the price times the power to get your cost in dollars per hour. And so if you do this for every point on the demand curve, you get a cost curve that indicates how costly it is to run your system at a certain price and power level. And to point out a few things about the linear demand curve, there is still no load reaction outside of the min-max price range. And any deviation from the mean price of 3 cents will cause a change in load. The purple indicator, or the purple arrows on the plot show that. It shows that a decrease in price will result in an increase in load, and an increase in price will lead to a decrease in load. And so as an example, during hour 13, the price changes from 3 cents down to 2 cents. And looking at the demand curve for hour 13, the purple arrow shows that it's pointing from the blue square, which represents the nominal load at the mean price, to the black square that shows that the load should increase by about 5 kilowatts. And this is confirmed in the top plot by looking at the black dashed line, showing that the load increased to 25 kilowatts during hour 13. So similarly for hour 17, our price changes, except we go from 3 cents to 6 cents. And looking at the demand curve, we can see that the arrow shows that it's going from the blue square to the black square. And this is showing that the load should decrease to its minimum. And this is because the price of 6 cents is actually above the maximum price. And so looking in the top plot, we can confirm this by seeing how the black dashed line overlaps with the red minimum line, or the red minimum load line. And so what we just saw is showed how the load can deviate from nominal based on the demand curve and how the price changes. And from a design perspective, this curve has the advantage of being simple to create because it's only defined by 3 inflection points. It also has the advantage of providing lighting service such that an incremental change in price will result in an incremental change in load. But by looking at the cost curve, it can be seen that the linear demand curve doesn't actually directly control for cost because the cost it can go up or down depending on the nature of the curve. So one way to control for cost is to keep it constant. So a constant cost demand curve can be designed to improve cost performance. And to design this curve, a target cost point must be defined. And here it's defined as the cost that's based on the nominal load at the mean price. And unlike the linear demand curve, we do not want to define a maximum and minimum price. Because this demand curve, it attempts to maintain cost until it reaches the limits of its flexibility range. And once that flexibility limit has been reached, a change in cost won't result in a change in load. And these limits are reached at different prices for each of these demand curves. So it doesn't actually make sense to define a minimum and maximum price as we did for the linear demand curves. And so the flat region on the cost curve shows that the demand curve is actually holding the cost constant for the price range in which the load stays within its flexibility range. And so this curve, it meets the design objective of controlling for cost, but how does it actually affect the lighting demand? And so to answer that, we can compare the load changes for the constant cost demand curve to the load changes for the linear demand curve. And so here, the linear demand curve for hours 13 and 22 are being compared to the constant cost demand curve for the same hours. And doing the comparison, it appears that for some hours, like hour 13, the constant cost demand curve, it produces a larger load increase when compared to the linear demand curve. But during hour 22, the constant cost demand curve produces a smaller load increase when compared to the linear demand curve. And so this is telling us that an incremental change in load no longer leads to an incremental change in price. And so the constant cost curve, demand curve controls for costs, but with the trade-off of having variable lighting service quality and a more complex design. And to summarize the couple of demand curves we just went over, the linear demand curve, it was simple in design and defined by its inflection points, where an incremental change in price resulted in an incremental change in load. But it did not directly control for electricity costs. The costs can go up or down depending on the nature of the curve. So next we looked at the constant cost demand curve, which was designed to control for cost, and it's a more sophisticated design driven by that cost management strategy. And it's defined by a target cost point and the minimax load limitations. And in the case of this curve, an incremental change in price no longer leads to an incremental change in load. All right, and with that, I'll hand it back to Michael so he can wrap it up for us.
Thanks, Shat. So we didn't have time to talk about the full scope of this particular aspect of the work. Additional details that we've analyzed include exploring how CLS might be configured to respond to other OpenADR signals. In fact, we looked at all the OpenADR signals defined in the 2.0 specification. And we also looked at the impact of other types of demand curves. There will be a report covering all aspects of this research that will be published soon on the Department of Energy's website, and so you're encouraged to check out this URL to look at the whole report. And if you would like to be notified when this report is published, you can sign up for email alerts using the link at the bottom of this page. That will add you to the Department of Energy's solid state lighting email distribution list. And with that, we would love to get any feedback you might have or answer any questions that you might have if we can. So please feel free to reach out to us at our emails below. And in closing, we'd like to acknowledge the full project team. So in addition to Shat and myself, Anae Weigel and Jamie Collin contributed to this work. Thank you for your time and attention, and have a good rest of your day.
Thank you, everybody.
All right. Hi, everybody. Thanks for joining in and listening. Don't see any questions here in the Q&A yet. Let's see about the chat. Yeah, so no questions here in the Q&A yet, but if anybody has any questions, feel free to drop them in there or hop in and ask us any questions. We're happy to talk more about it. Still there, Michael? Looks like you're frozen. Yes, okay. Gilberto, I hope I'm saying that right, has a good question here. He says, great tool with very wide applicability. How do users get access to implementing something like it? So by tool, I'm assuming you mean, and implementing something like it, I'm assuming you mean implementing OpenADR. OpenADR, it's an open protocol. Anybody can design to the spec. And there is a certification process that you must go to actually be certified as an OpenADR compatible device. You can read the spec, and if you're a company or somebody that's interested in developing VTNs or VENs to be used for whatever it may be, you just design your product to the spec and have it certified through the OpenADR Alliance, and then that would be how you would go through that process. It's a good question. Thanks.
Am I back?
Yeah, it looks like you're back.
Gotcha.
Yeah.
And one thought, I'm not sure if Gilbert was really asking about certifying a product or if he was asking whether we are developing a design tool for people to create demand curves. And the answer to that question, at least right now, is no. That tool, if you will, is something we're just using to explore different design demand curves and what the expected response would be to of those ideas and implement them in real-world connected lighting systems as they allow, and see what the response looks like. I think that's something that we might consider in the future. So it's kind of an interesting question from that idea. DOE and national labs have developed tools and released them to people in the past, and based on opportunity and interest, we could consider that here in the future. And I think it's, oh, nope, still 2 people left.
Yeah, it's kind of funny. It says 2 people in there, but then there's a little eyeball up top that says 6.
Yeah, well, when you click on people, it says 6 still, although 2 of them are with the...
Oh, yeah.
With the Linux folks.
Right. For everybody that's still with us here, it looks like we're about at the end of our time. But if you think of any further questions, feel free to reach out to us, and we'd be happy to talk more about it. So thanks for coming, everybody, and have a good rest of your day.